First thing I want to talk about is the big O notations. And they were all really good. Seemed like everyone was working well together in groups. I didn't get the score of a one when we did the peer evaluations. Hopefully, everyone was honest with the peer evaluations. Um, but I hope you enjoyed doing it. I hope you learned something, even if it wasn't about big O notation, about how you made your video, working with people, maybe made a connection with somebody that'll carry through. But one of the things in the big O notation was, and it was about 10 years ago, I was at a conference and I'm sitting beside somebody at a session and they said, "Oh, good Lord, they're reading their PowerPoint to me." And it got me thinking, yeah, that's not so good to just sit there and read the pages that I'm looking at. And if you think about it, that could become kind of boring. And when I put something like what I have on here, I shouldn't be reading it to you, but it should be parts of what I'm discussing. So if you're ever doing another presentation, and a couple groups did this, don't do the here's your screen, all I'm doing is reading it. You could read parts of it, like we're going to talk about a directed graph today. And that's a graph that has directions. It's a little different than what we've been doing with trees because instead of going to two different nodes like in a binary tree or going to, when we had the m's and we went to the m minus ones number of nodes and so forth, we're going to have kind of like nodes and we're going to be able to go from that node to zero nodes. Might not go anywhere. It might go to just one node. It might go to a bunch of nodes. So instead of that tree look that we've had, we're now going to have a different type of look. All right. So what do we have? We have a directed graph. That means there's going to be directions going from one to the other. And a big example that's common and it kind of makes sense. It's like the hello world. What you would talk about is an airport. You could build an airport and right now you're still building it. It doesn't go anywhere. But you could also build an airport, and the airport, let's say Harrisburg, could fly to Allentown. Harrisburg could fly to Baltimore. Harrisburg could fly to Pittsburgh. Baltimore might not fly to Harrisburg, and that's okay. But we got these directions going. So start thinking of I'm going to throw airports on a map of the state of Pennsylvania and who flies to each other within the state. All right. So we don't need a route. It's just a map of all of the airports. There can be several or no paths from one, here we go, vertex to the next. So instead of nodes, we're calling them vertex, and we got paths going on and some different language. Another thing that we're going to briefly take a look at is a graph. Just a straight up graph has no directions. Doesn't do us much good, but we're going to take a look at directed graphs today and a little bit on Wednesday before we wrap everything up. Okay. Digraph consists of, now I'm reading, finite number of vertices. Vertices are 1, 2, 3, 4, 5, and 6. That should be well highlighted. Vertices or nodes, we've been calling them nodes. And then it has a finite number of edges. Sometimes they're called directed arcs. This comes from something called graph theory. I had a grad class, Millersville, graph theory. It's pretty darn cool. You start getting into things and can you draw this envelope without lifting your pencil, without crossing over what you're doing? And graph theory gets into wait a minute, this is a node, this is a node, this is a node and a node. And then I have, okay, so this graph, can you do it without listing? And you get into all this. This has two edges coming out of it. This has one, two, three, four. This has three. This has three. This has four. And the theory is as long as you have an even number of odds, you can draw this graph. So here's a three and here's a three. Now, let's see. I should be able to graph this over, over, down, crossed, up, over, down. Ta-da! I made the envelope without listing my pen. There's a great problem that you would see in a graph theory book right away. It's the bridges of Königsberg, something along that line. And it talks about having these bridges going from all the different towns. And within those towns, can I get from one to the other, to the other, to the other, to the other, and move around like I was doing here? And when you look at those bridges, you're going to end up seeing you have an odd number of odd nodes with arcs coming out of it. So it's an unsolvable problem. But it's like really famous if you start talking about graph theory.
Why wouldn't the one in the middle not be a node?
So you're saying, so what if I did this? Didn't, didn't, and jumped over it. There was a bridge over that road. So this is an underground train to get here. This is a bridge above or a road above ground. So just because they crossed doesn't necessarily this means has to be one. Could it be one? Sure, it could. But we could have one going here and then ding underneath it so that they don't actually touch. Graph theory. All right, let's see what I have. I wrote that down, and there we go. I have 6 cities. So we're going to start out with this basic idea of a directed graph. And as you can see, I can go from one, and I got two. Can I get from 1 to 6? Is a question. Can I get from 1 to 6?
Yes.
Yeah, Scooby.
No.
Oh, okay.
Not with these directions. I can go 1, 4, 3 or 1, 2, 3, but I get stuck there. You know, now, so the first one is can I get to somewhere from somewhere? The second question is shortest path. What's the shortest path? And that's we'll get into that a little bit more Wednesday. So we got this idea of a diagram. All right, so now let's go back to what we've been doing in this class. What would be some functions? If I wanted to do all this, what would be some functions? Well, I could insert a node. I could delete a node. I could insert one of these edges. I could delete an edge. I could possibly find out what does exist, what doesn't exist. That was our old school is empty. Okay, so I was mentioning a moment ago the shortest route, just like today. I'm assuming it's still that way. But when FedEx first started, they were saying, here's your packages. What's the shortest route? You know, think if I have to go to all these different places, how would somebody calculate what's my shortest driving route? Well, I do know one of the other factors that they put into that was eliminating left-hand turns because left-hand turns take longer. So there's all of this stuff going on. What other things? Well, those paths we saw might be weighted. We only have certain extra large planes that fly from here to there to there, but you might want to take a cheaper plane that might take longer. Price is an issue. Layovers an issue. Start thinking of all these things with planes and oh, how did they figure all this out? We can put in a node with no edges. We're still building the airport. We can insert an edge between two existing nodes. We are now flying to check out number 3. Make up a story for number 3. Stick with planes. Where's this
What
plane?
if it
You got Jack?
back to where it started? It
Yeah,
could have ran out of fuel.
could have ran out of fuel. It could be a training facility. Got lots of things going on. It could be a pleasure thing where you just get up and you fly around a little bit and you want to be able to re-land. I don't know. You could make up all kind of stories. We're just talking in general. Okay, down here, the operations. We learned about a topic. We talked about what operations it would be. And then we moved into how in the world would you store this information? How am I going to store this? Okay, well, let's draw one. Going to go around in a circle. A, B, C, D, and E. That's not too bad. Let's say A flies to E. That's cool. D doesn't go anywhere. C goes to D. B goes to C, and C goes right back to B. A goes to B. A goes to C. Nice and simple. I like it. So I have this graph. If I said, where would you like to start? You would say A, but A is not a route. We don't have a route anymore. I could start in B. I could live near Baltimore. All right. How can I store this? Well, our choices so far have been an array or some type of linked list. Well, this first one, we're going to sort of store in an array, but we're going to call it an adjacency matrix. We're going to take a look at a matrix. This is the adjacency matrix representation. Follows the same darn pattern we did this entire semester. What do you mean a matrix? The matrix, yeah, wong, wong. I'm going to put a list of the cities. A, B, C, D, and E. A, B, C, D, and E. Let's see. I'd like to see if A goes to A. And it doesn't. So now I need to put something in here. 0. A goes to B. 1. A goes to C. It does not go to D. And it goes to E. Where does B go? B goes to C, and that's about it. C does a little bit. C goes to B, and C goes to D. D only goes to himself. And if you go to E, you're stuck in E. Next week for the final exam, it's going to be hard to type some of these things in. What you can do is do it on scratch paper. Where the problem is, put C notes. And then what you're going to do is take a picture of this, and over in the Dropbox, you can upload it. I do that with all of my math classes. I have everybody make it a single PDF and upload it. And then when it says see notes, I go and look at the notes, and it might be easier for you to do by hand. So I'm letting everyone know. Okay, so we got that. I could build an array. If I said I now want to have a flight from C to E, change that from a 0 to a 1. And that's all good. So I do know a little bit about matrices. I know how to add matrices. I know how to multiply the matrix by a number. I know how to multiply matrices. Maybe I do, maybe I don't. I'm going to write the matrices. 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0. I like to hear myself talk, even though I'll probably lose my voice again. That's my matrix, and I'm actually going to write it again. And I'm going to go back to old school multiplying these two matrices. Used to be something we had in our college algebra course. It's not around anymore. Okay, so I need to fill in these first 5 numbers. And these locations are row 1, column 1, row 1, column 2, row 1, column 3, etc. So the way I do this is, this was row 1, column 1 is going to be this first guy right here. I'm going to take row 1 right here and column 1 and combine those by multiplying to get an answer for in here. Now, I take the first element times the first element, 0 times 0, plus 1 times 0, plus the third item is a 1 times 0. The fourth element is a 0. Oh boy. And the fifth element is a 1 times a 0. So I took row 1, I multiplied it by column 1, and I got 0. The next one I'm filling in is row 1 times column 2. This time I'm taking this column. And I got the idea. 0 times 1 is a 0. 1 times 0 is a 0. The third one, 1 times 1 is a 1. 0 times 0 and 1 times 0. This guy became a 1. Excuse me. Row 1, column 3. You got an answer? 1. Okay. Row 1, column 4.
0.
I think the third one here's a 1, and the third one here's a 1. So I think that's going to end up being a 1. And the last one's a 0. Next up is row 2 times column 1, and then go through. Take a second, see what you can get for that. I'll throw an answer on there, and we'll see if we have questions. So now it's row 2 times column 1. That looks like a 0. Row 2, column 2, that's a 1. What's the maximum number I might accidentally get in here?
Two,
Higher,
3.
higher?
Theoretically, it's 5, but we don't
Yes.
have any of the rows that are all ones.
Right. It could be as many as 5, considering we're working with zeros and ones here. So just because right now these are zeros and ones, let's not fall into the trap of thinking that's what they are. This could be much larger. That's a 0. That one's a 1. Row 2, column, and that's a 0. Speak up if you want me to do a third row. Okay. So what does this mean? What does this 1 mean? That, when I looked at my original matrix, this was A and B, this was A, B, and C. Well, I'm going to tell you. If I start at A and I want to go to C, I can get to C. Yeah, but I can get to C this way. This guy is a representation of path size 2. To get from B to D, there is one way with a layover. To get from B to D, there is one way with a layover. It's a path of 2. Right? Ah, that cute. If I wanted to see paths of size 3, I would take this path size 1 and multiply it by a path size 2. So this representation was path size of 1. Wow. Now in my computer science world, I'm starting to put a bunch of things together. How would I represent it? How would I move about? How would I add something? Well, I think I would have to create my original 2-dimensional array of size something bigger and then keep track of size and how all that works. Could there be a lot of zeros? Yeah, could be. We have a start now. We have an idea of how to store this data, start to have an idea of the functions that would go with it. What would I do? I mean, if I want to add a flight from C to E, I can go in and put a 1 in. It currently does not exist. I can't get you to E, but maybe I can get you to E a second way. So now I'm starting to talk about how I would traverse this. I can't get from B to B unless I take a path of 2, which means I go from B to C and C right back to B. It's kind of clever. Not sure who came up with it, but it's kind of clever. So number 1, there's our arrays. We used a 2-dimensional array. We like to call it a matrix. Adjacency matrix. Can I move on? We good? Second way. It's kind of almost named the same thing, but this time instead of matrix, we're going to do a list. Yeah, that's a word we used quite a bit throughout this course. Let's go back to my drawing. A, B, C, D, E. A went to B. A goes to C, and D goes around in a round and up and down. And nobody, oh yeah, A goes to E. Only the A's can get to E.
So in that adjacency matrix, the column for A will always be straight zeros because you can't ever get back to A, right?
X. Column for A was straight zeros. Now that was for a path of one. As we look, that would be for all paths. Yep. What do you know about the row for E? Row E goes nowhere. So that would always be zeros.
Well, wouldn't E always become a zero even in the column as well after the path of one since A is the only one that goes to E?
Um, let's see. Can I go to A and get back to A? In this case, you're correct. But there may be a way to get back to A and then over to E. So it could be a path larger than that. That could be a spy, and I don't want to go right to E. So I pretend like I'm leaving and I'm hiding and I'm hiding and I'm hiding. And then I get back to A and can sneak over to E when they're not looking anymore. Dude, adjacency list matrix. Let's see what's going on here. Um, linked list. No, it just we learned linked list, but that's not going to help. Is there something we may have learned that might help here?
Chaining?
Chaining. Yes. How about and array sub one is A, and A goes to B, and that goes to where else does A go to? And it goes to C, and it goes to E. Yeah, we know that concept. B goes to C. C goes to B and D. Yeah. D, where's D go? D goes to D. I think I like the matrix representation better. Not sure where I might go after this.
E doesn't go to E, does it?
Nope. I just made that up. Where does E go? No. Thank you, Andrea. Do 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 do. Isn't that just Purdy? I don't know what all that is. We got some stuff going on in the book. Yeah. Oh boy. How'd you draw the matrix for this? The two-dimensional array. Yeah, we could do the adjacency matrix. I'll be okay with all that. Do this, take a look at number 5. So what you will see is this matrix in number 5, and we're going to say we're going to multiply it by that A, B, C, D, E, and how it would represent and what it would look like. So as you're starting to see, there's lots and lots more we could go on here. We're not going to delve too far. But what this is saying is, can you draw the directed graph for this? Can you draw the directed graph? Now, I wrote the A, B, C, D, E up here and here, but this is how it would be represented going backwards, I guess you could say. So all of a sudden, I'm going to go draw the directed graph. Okay. A, we can go around any way we want. B, C, D, and E. A goes to B and D. A goes to B, A goes to D. D goes to A, B, and C. B goes to itself. B goes to C. C only goes to E. D goes to B and E. D goes to B. B's pretty popular. And E goes nowhere. What you think about that?
Wait, C goes to B, right?
C is this row. So if I wrote it here, A, B, C, C only goes to E.
Gotcha. Oh, I misread.
Da, da, da. Oh, there's an adjacency matrix. Could you draw the picture from this? Yeah. Nodes in this case are called 123. 123 goes to this guy, 45, and it goes to 999. So we have one node is 123, one node is 45, one node is 176, one node is 303, and the last node is 999. And this goes to the second one, which is 45. That's the visual I need before I can start working. I need to draw. Conceptually, are we good? Okay. Conceptually, can we find our bookmark? No, there it is. Do, do, do. I got stuff going everywhere. Part two. So we came up with, I don't want this anymore. I don't want that anymore. Alrighty. So some of our functions that we have, and a big one was the ever popular searching or traversing. And we had different ways with our binary search tree. We had prefix, postfix, infix type of searches and so forth. But in order to do searching here, we need to go back to a basic drawing before we can move on. So this first idea is called a breadth search, a breadth first search. And I'm going to start with a tree that looks something like this. This is a breadth. Now, a breadth is going to be a search where I start at A and I go one trip away. I'm going to go from A. I can get to B. I can get to C. And I can get to D. Now, with this breadth search, A is done. I made a list of all the places it could go. So now I move on to B. B can go to E. B can go to F. I'm done with B. I jump to C, goes nowhere. I jump to D, it goes to G. I go to E, it goes nowhere. F, it goes to H. G goes nowhere. H goes nowhere. So this is an example of a breadth first. And I start with, I should have put arrows in because arrows here would make sense because that's the direction I'm going. Okay, so I'm going to draw another one. This time it's not going to look like a binary tree with a root and so forth. This time it's going to be a mess. And I have A, B, C, D, E, F, G, H, and I. And now let's make it a directed graph. A goes to B, A goes to D, and A goes to E. B goes to F. C goes to B. C goes to D. D goes to C. D goes to H. E goes to H. F goes to G. F goes to I. G goes to B. G goes to C. H goes nowhere. I goes to H. Okay. First question, doing this by Brett, Breadth. First method is, where do I start? Where am I starting? I don't know. You tell me. Where are we starting?
Start anywhere, right?
We can start anywhere. So pick one.
G.
G. Go one away from G. Where can I get to?
B and C.
B and C. Go to B. Where can I go one away from B?
F.
Yep. I think B is done. If we go to C, where can I get to from C?
D.
I can get to the D. And I'm done. F, where can I get to one away from F?
G and I.
E and I. D can get me to,
H and C.
but I already know I can get to C. So D can get me to C, that's correct, but it can also get me to H. So what I'm looking at is if I start in G, this is all the places I can get. When I did the from G, it was B and C. They were each like one path away. Then I went to the B and said I can get to F. That's two paths away. I went to C and said I can get to D. So this was like two paths away. Now I move over to the F. This is going to be three to get to G kind of idea. And it's going to keep growing. G can get to B, which is already on the list, and C. I can get to H, but I can already get there. And H can't get me anywhere. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. Oh no. If I start in G, I cannot get to what letter?
A or E.
A or E. Oh man. I can't get to A or E. Yeah, I don't know why I have G in here a second time. That was a goof up. Yep. Can't get to A or E. So if I'm at G and I want to get to D, I know it's a path of two. G to C to D. I think when we started this I, that came off of the F. So that was a 3. And then we went to D, that could get me to H. That was a 3. So next would be from I, that would be 4. Oh, these airlines, they've got a lot going on. Could be multiple flights in a day. Could be different airlines. Well, they probably don't care about each other. Brett first. Brett first.
So in this case, if we're tracking how many steps it takes from G, it takes 2 steps to get back to G, right? Because you go to B to F to G, or actually
We
three
would have
steps.
we would have left, we could have left that in there and tracked all of them. But we're trying to get through and see where all I can get right now.
Gotcha.
But yeah, this would be something you could add on. Yeah. So that was the first one, breadth. The second one is called depth first. Traversal. A, B, C, and D. And this might look a little familiar, but the depth is going to go deep. Go deep. Start at A. I'm going to go to B. I'm going to go to E. I can't get anywhere else, so I backtrack. Can I get somewhere else from B? Yes. I can get to F. I can get to H. Nowhere backtrack, nowhere backtrack. Back to B. Nowhere backtrack to A. Start going deep. Depth charge. Back to A, to D, to G. Again, this one is called depth first. Go as far as you can and start to backtrack. Each time you backtrack, go as far as you can. Well, let's look at our big picture. We had A, B, C, D, and E. We had G. Oh, excuse me, that was F. F, G, H, and I. A went to B, D, and E. B goes to F. C went to B and D. E went to C. D went to H. E went to H. F went to G and F went to I. Z went up to B. G goes to C. I goes to H. Depth first. Pick a letter to start. Pick a letter, any letter. Pick a card.
Go A this time.
Let's go A this time. Okay. Could there be different answers? Yep. A goes to B. F. A to H. Stuck. Go back to I. I'm stuck. Go back to F. I can get a G. G goes to B, which is already on our list. G goes to C. I'm done with G. So I go back to F, go back to B, go back to A. A goes to D. D goes to H. I already have that. Go back, go back. A goes to E. From A, I can get anywhere.
I feel like I'm maybe misunderstanding something, but why would you, when you get to G, why would it traverse back instead of just like traversing forward to C?
Well, when you get to G, it says go to C, which it did. Go to B, but we were already there.
Gotcha.
Yeah, keep the binary tree out of mind. Eliminate thinking this way. Because we could have this. This was just a simplified example. Want to try another letter? Sure. Let's just go with G. G.
Is it arbitrary which direction you have G start?
Doesn't
Like G.
matter.
Okay.
It's totally random. I went to C. I went to D. I went to H. That's it. Back to D. Back to C. C actually goes to B. B goes to F. G. I. That's about it. G can't get to A. G can't get to E. I think we saw that in our previous example as well, when we did the breadth search first. The breadth is the nicer one because you get that whole one layover, two layover type of thought going. Excuse me. Questions? Comments? We are going to stop there. I don't know that my voice has much left. But pie graphs. First big idea was how to represent them. Matrices, chaining. Second idea is traversing them. Breadth first, depth first. Are there any questions? Concepts are good?
If you were backtracking, like you go G, C, D, H, you backtrack to D, you backtrack to C, would you then go to B or would you backtrack to G and then go to B
You want to keep going as far as you can.
before you have to backtrack? So then you would go C, B.
Yeah.
Okay.